Looks like people are just... Welcome everyone to the second talk in this seminar series, Tunneling in QFT. For those of you that missed the first in the series, this is a once-a-month series on this specific topic of tunneling in QFT, whether like vacuum decay or maybe Schwinger pair production, all kinds of possible things along these lines. For those that missed the first seminar by Ian Moss, or would like to rewatch it, it's available on YouTube. We have a YouTube channel and you can find the link in the Indico page. Today, we're very pleased to have our speaker, Silvia Pla Garcia. Sylvia is a postdoc at King's College London, having completed her PhD at the University of Valencia. Sylvia is an expert on QFT and background fields in a variety of different topics and directions, but in this field, she's worked on tunneling in a range of things, starting from, well, including Schwinger pair production, the production of charged particles in electromagnetic fields, and production of particles in gravitational fields. And more recently on vacuum decay in the presence of non-trivial space-time metrics. And I think it's that topic that we're going to hear a bit more about today with the title, Can Quantum Tunneling Induce a Cosmic Bounce? So yeah, please take it away, Silvia.
Okay, hello everyone, and thank you for the nice presentation. Okay, so today I'm going to talk about this topic. So the title of the talk, as you can see, is Can Quantum Tunneling Induce a Cosmic Bounce? So I will try to answer the question in the affirmative. So yeah, I'm presenting basically work I did with some of my collaborators, Jean, Drew, Katie, and the talk is based partially or mostly in these two articles. Okay, so let's start. First, before starting the talk, I want to say some things to clarify what I'm talking about. So first of all, what's the talk about? Like very briefly. The talk is about the violation of the null energy condition because of quantum field theory, in this case via tunneling, and the consequence in cosmology. So I would say that the main formula of the talk, the most important formula is this formula that you see here. So what I will try to explain you is that when we have, when in the context of finite volume, and when we have non-trivial classical potential or classical configuration or background configuration, we have a shift in the vacuum energy. So we are used to listen that when we have quantum fields, the vacuum energy has a contribution to the cosmological constant. So I will try to show you how, when the external configuration is not non-trivial, like in this case, where we have this process, the cosmological constant suffers a shift and changes. So we don't have a vacuum energy which is a constant anymore, but we also have this correction, which can potentially be very relevant in cosmology. So we have this sign, this Q that depends on the parameters of the theory. And then we have these factors here that are related with the external conditions, in this case, the volume of the space. So this talk, I'm a bit afraid, is not about false vacuum decay, because we will be working with two degenerate minima and infinite volume. So it's not about double nucleation, and it's also not about the sitters. So it's about tunneling, but maybe in a different context that I think it can be nice for this conference series. So why is it important? Okay, with this sentence, I try to be a bit like maybe optimistic. I would say it's to save the universe, but I will explain what I mean later. I will explain that having some known mechanisms in quantum field theory that violate the net can help in building a consistent cosmological model, if you want. But okay, this sentence maybe is a bit too much. So, and this is the overview of the talk. So as I showed you before, this is the title. So I will try to explain you how quantum tunneling can induce an effective vacuum energy that differs from the standard one, because the external conditions are different. So it's different. And how this vacuum energy can help us in inducing a cosmological bounce. So I will focus both in the cosmological implications and also in the field theory details, because I think they are different from the standard picture in false vacuum decay. So I think it's interesting to show you some details. So first, so I think The order of the talk, it will be a bit different than usual. So first I will show you the main results, the main formulas, and the thing that I want to explain, the main ideas. In the second part, I will show you some results about cosmology. And in the third part, I will focus in the quantum field theory side. Maybe this part is a bit more technical, but I think it will be fine. Okay, so far so good. So start with part one, introduction, assumptions, and main results. Okay, so before I start with the first part, I want to say a couple of things. And the first is that the framework in which we are working, in which I computed this, we computed these results, is, well, it's quantum, I would say it's quantum field theory in curved space-time. So this framework or this theory studies the behavior of quantum matter fields propagating in a non-trivial background, generically speaking, a gravitational background. But these quantum matter fields are like test fields. So they don't have the ability to back react with the space-time. So they are like just propagating there. And the idea is to study how standard quantum field theory changes when we have a non-trivial background configuration. Okay, this is the first step, but there is also a second step, a second layer in the theory, which is what we call semi-classical gravity. And semi-classical gravity is about studying the back reaction problem. So it's about how the quantum effects that we compute in the first layer can back react to the background configuration. So the background metric, for example. So if we have a process where particles are created, we can ask, how can these particles back react to the background metric? So to deal with this problem in gravity, we need to solve the semi-classical Einstein equations. So here we have the Einstein tensor. Here in the matter sector, we include in a self-consistent way the term that comes from the matter degree, the quantized matter degree of freedoms. So here I put these symbols here because, like, when we work in semi-classical gravity, we have to add like higher order derivative terms in this side because of renormalization, consistency of the theory. But okay, it will not be important for this talk. So this talk, it's about both layers. So to compute the effective theory and the quantum tunneling that I will explain you later, we work in the first layer. So we assume a given background configuration and we compute some effective theory. And then the cosmological implications or the cosmological effect is about semi-classical gravity. It's about how this effect can back react once it's computed with the background metric. So this talk is really in these two frameworks. Okay, the last thing that we need to know about to understand the talk is the concept of the idea of these energy conditions. So I think we all know a bit about the singularity theorems that are these theorems that in general relativity that show that singularities in general relativity, but in particular in cosmology, are inevitable under very general circumstances, like they appear. However, we are kind of lucky because they have in their assumptions an important restriction on the energy momentum tensor of the matter degree of freedoms, which is that, well, it's the strong energy condition, but we are fine only looking at the null energy condition. So the null energy condition is a condition that the matter degrees of freedoms are supposed to assume. That is this condition that you see here, that the contraction of the stress energy tensor of the matter fields with these null vectors is greater or equal than 0. So for a perfect fluid, that is the case that maybe we want to know about in cosmology, the null energy condition reads like this. So what is important here is that it's well known that the null energy condition can be violated by quantum fields. We know some cases in quantum field theory where this condition does not hold. So I would say that's kind of nice because in this context, then singularity theorems do not apply. So then we can maybe avoid potentially the singularities that we commonly have. So the question is, if the null energy condition is violated, then can we avoid this cosmological singularity, this initial singularity? So I will try to answer that question of course, for this particular case. Okay, we are ready to start. Now I'm going to tell you about the main or the highlights of the work we did, and then I will give you some more details. Okay. So the starting point is, as always, to compute this quantum effect, as always, not as always, several times, a real scalar field, in this case, in a double well potential, the one you see here, with 2 degenerate minima. That's kind of important, in finite volume. That's crucial for the effect that I'm going to show you later. So that's a restriction in the cosmology that we are analyzing later. And we also have, well, we also can have in this problem an external slowly varying Friedmann-Robertson-Walker background. So this is the potential that we have. And here we added a constant, which is like the origin of energies. And I just have written it like this for later convenience, okay? But okay, the most important part is this part, this double well potential with 2 degenerate minima. So in this context, when we study the quantum theory associated to this potential, we know that quantum tunneling can happen between these two degenerate minima. And then it gives us an effective theory after integrating out all these quantum fluctuations. It gives us an effective theory that is quite different than the classical theory. So we know, well, we can compute the effective potential when we consider one loop fluctuations, and when we consider tunneling happening between these 2 degenerate minima, and we arrive to an effective theory that is very different to the original one. The effective potential looks like this and has only one minimum, which is located here at phi equals 0, and it has non-trivial energetic properties. In particular, the vacuum energy after doing all this process is non-trivial. So, okay. In particular, the effective potential, when we consider all this quantum process, looks like this, but we are interested in this U0, the vacuum energy, the minimum of the potential, and we compute it, and we saw that it looks like this. So we have a constant, this origin of energies that also appeared in the Baire theory, but here we have a correction. This correction is quite interesting for many reasons. First, we have a negative sign here, then here in the exponent, and also here we have something that depends, well, on the co-moving volume, on the volume of the space that we are considering, of the closed universe that we are considering. And this R is a coupling that depends on the parameters of the theory. So from this result, we can study the energetic properties of this minimum of the potential, of this vacuum state. And we can compute the energy density and the pressure, and we realize that it violates the null energy condition for any value of V0. Of course, the effect is suppressed for very high volumes. So I would say, yeah, we need this finite volume to achieve this effect. So then, since it violates the null energy condition, it's a good candidate to induce a cosmological bound, so avoiding the initial singularity. So once we got this result, we couple it to the metric via the Einstein equations, and we saw that indeed we are able to avoid the singularity when we start from a contracting phase, so finding cosmological bounds. So I will tell you more about these cosmic bounds, but first I want to be clear about the assumptions that we made to arrive to this final result. So the main assumption that we took is the finite volume assumption. So to compute this effect, we need finite volume, and because if not, this effect is suppressed. And then we also need, we need also these 2 degenerate minima. So since we wanted to focus in the effect by itself, we ignore some complications. Like, for example, we neglect spatial curvature. We assume that momentum quantization can be ignored, so we ignore the Casimir effect. We assume that boundary conditions do not play a role because we really want to see let's say, the key point. But of course, now we are working in improving all these conditions here. The second assumption that we made to derive our result, in particular to derive the effective potential, is the adiabatic approximation. So we assume that the expanding rate of the universe is super, super small compared with the tunneling rate, which we assume to be instantaneous. So in practice, we set the scale factor constant when computing the effective theory, and we just restore the time dependence when we went back to real time and couple this effect to these inequations. So of course, that's a big approximation and we should think about some improvement. And finally, well, this third point is related with the second point. We work with quantum field theory in equilibrium. So we work in the path integral approach, in the in-out formalism. So we have to perform a weak rotation as usual to study this quantum tunneling. So it means that we work in Euclidean time. Okay, so that's the main idea of the talk. So we start from a double well potential, infinite volume with two degenerate minima. And when we study the effective theory, we see that it's very different. It has only one minima and it induces a vacuum energy that is not trivial anymore. And in particular, it violates the non-energy condition. So then I said that this can induce a cosmological bound. So now I'm going to talk a bit more about the bounds. Okay, so the main result that comes from the first part is this result, this vacuum energy, meaning this is the minimum. So we have the standard constant that we always have, and this shift with negative sign, exponential suppression, and this term that you see here. Again, this alpha is related with the scale factor, and this S0 is proportional to the volume cell of the space-time, of the space, and this is a coupling constant. In particular, we compute from this because this has the form of an homogeneous perfect fluid. So then we can compute the energy density and the pressure associated with this vacuum state. So we can compute easily, we can compute them. So then we can couple this fluid to the Einstein equations and see how it looks. So those are the Friedman equations. We put here our results from the previous slide, and we check that for different values of R, where R is the coupling, if we start from this initial contracting phase, we always reach the bounds. So here is the scale factor, and this is the Hubble rate. So for example, here we start from a contraction, and we see that we always cross zero, and then we start growing. And then what happens is that this extra effect that we have, this extra effect is exponentially suppressed. So we end up in a de Sitter phase because in the problem that we are solving, we only have the cosmological constant and then this extra correction. So of course, this is what makes sense.
Silvia, we have a question in the room.
Yes.
That's okay. Lucian?
Yeah, thank you. Hi, Silvia.
Hello.
When you talk about the effective theory, is it a one loop result or is it the full effective?
It's one loop. It's one loop. So it's one loop, but with some non-perturbative cuts. I will explain you later. But
okay.
Let's say one loop.
Okay, thanks.
Okay. Okay, I'm continuing. So, okay, we test, we test our solution and we found these bounds, but of course this is a super simplified result in which we just wanted to test the effect, the pure effect of this ground state fluid that we have. But okay, then we said, how can we easily test these cosmological bounds that we have? We have many ways to test it, but we thought that it could be interesting to add a second component, so like a second matter field into the Friedman equations to see the competition between this vacuum ground state fluid and this new second component that we add. So we decided to add an anisotropy. So we decided to add to work in an anisotropic universe because I think that's as I will show you later, that's the most important component when we are close to a singularity. So it's the one that will fight the most with the effect that we have. So to keep it simple, we decided to work with a Bianchi one metric. So it looks like this. So in this context, it's very, very convenient to work with average quantities. So now this A is the average scale factor, this H is the average Hubble rate, and we have a new parameter, well, a new quantity is this anisotropy here that is telling us the amount of anisotropy on average that our space-time has. So in the simplistic configuration scenario that we derived before, we realized that then if we work with this metric and assume a constant. The only change that we have in rho and p is that where we had the standard scale factor, now we have to substitute it by this average scale factor. So working in these terms is very, very convenient, because then when we go to the Friedman equations, we realize that they look exactly the same, but with this extra term here and this extra term here. And in fact, it's easy to check that this anisotropy behaves like an homogeneous fluid with equation of state W equal 1. So in fact, from the defining equation, we can see that it scales like this. That's why it dominates the fastest or the more during the collapse. So then when we add the anisotropy, this situation is much richer. Why is it? So because in this case, the null energy condition, when we consider the full stress energy tensor, is not always violated. It's sometimes violated and sometimes satisfied. And this condition allows us to find a static solution to the Friedman equations, a solution where we have, let's say, a closed universe that is static. It's unstable, okay, by the way, but it's static. So this critical solution can be found by imposing this condition that you see here. And this condition fixes us the size, if you want, we can identify alpha with the size of the universe at the bounds. So the solution after some analysis is giving us the minimum value that the scale factor or the universe can have, if you want, for the bounds to succeed. So how can I explain it? So if we, like at the moment where h is equal 0, if the size of the universe is smaller than this, we will have a crunch. And if the size of the universe is greater than this value, we will have a bounce. In terms of the anisotropy, is the opposite. Like if the value of the anisotropy at this critical point, if the value of the anisotropy is higher than the critical, we will have a crunch, because then the anisotropy dominates and doesn't allow us to bounce, okay? So it's interesting that the critical point, as I explained you just now, is unstable. So so it's something that you only can find if you really fine tune your initial conditions, but actually it's something that is just unstable, because as I said you before, a value slightly smaller will crunch, and a value slightly larger will bounce. Okay, we can also infer the maximum value, just ignoring the anisotropy and finding the result that we had before. So actually this equation, is giving us the size of the universe, well, this kind of size of the universe in terms of the parameters of the theory R. Okay, and here the same for the maximum value. Well, it's interesting to see that in this simplified model, they are of the same order. So we try to play around with the parameters and to do some pheno, but of course it's a toy model. So I'm not saying anything about real physics, but just to see. So as I said you before, this critical value can be related with the size that the universe should have at the bounds. So here I did a plot just to make some small analysis. So in this plot, what you can see is in the x-axis, the mass of this real scalar field that we have. And in the vertical axis, we have the size of the universe at the bounds. And then here we have this vacuum energy that we can interpret as the cosmological constant if you want. So of course, this coupling R is 3. So let's focus in R equal 1, which is the blue line. So if we want our universe at the bounds to be of 1 meter, which is here, it means going down that the mass of the real scalar field should be of the order 10 to the minus 7 eV. And then if we go up, we realize that the vacuum energy should be super small, 10 to the minus 140. So in general, we play a bit around with some parameters, and the conclusion is that in this very simplistic scenario, so I'm not telling anything about physics at this point, but this model tends to favor small masses for this field, small sizes of the universe, or small values for the cosmological constant. Okay, but of course, as I said before, this is a toy model, so I'm not actually saying anything about real physics. Okay, I think I said maybe enough about the cosmological implications. So the key idea that maybe you can take from this result is that we found that in fact this vacuum energy, which is non-trivial, can induce a cosmological bounce. In this ideal situation, it happens always. But as when we start to add other matter components to the Friedman equations, the situation is less ideal, let's say, and the bounce is not guaranteed, because then if the matter components are like dominant, they will force the collapse, let's say. But well, yes, that's it. Then part 3, let's talk a bit about the effective theory, because so far I only showed you the results, but I guess some of you may be curious about how we did compute this result, because I think it's kind of interesting. So let's focus now on the effective theory. So in the following part, I will explain you how we did it. So I will not be very, very formal. I will be like, I want to be pedagogical. So yes, that's, I think it should be fine. So the starting point to compute the effective theory and this non-trivial vacuum energy is this real scalar field, this classical theory. So we have, as I told you before, a real scalar field in this double wall potential with 2 degenerate minima. So we don't have any false vacuum decay because they are both equally important. And we have finite volume. So we need the finite volume for this effect to be relevant. Yes, that's it. We also add this constant term, which, okay, is the origin of energies, but let's say that when we do renormalization, it's kind of required. And also, this is more technical, but to compute the effective theory and not only the vacuum energy, we need to induce this source term that is the one that will allow later to compute the effective theory. So how do we arrive from here to this effective potential? So the way we do, as I told you before, is using the path integral formalism, the in-out formalism. And then from this, we will apply standard techniques from quantum field theory. So the first step is to find the partition function describing the system in Euclidean time. Okay, so how do we do this? So here we are in a very nice situation, because it's a situation where we have different classical solutions or saddle points, that I will show you later, that are relevant to the partition function. So we have to work in this so-called semi-classical approximation, where we assume that the partition function can be split as a sum of the partition functions associated to each of these classical configurations. Okay, so maybe that's a bit hard to understand, but you will understand me better after reading this. So we also work in the saddle point expansion. So we will work in one loop, in this one loop expansion. So we will assume that the field can be expanded as classical field, classical solution, plus quantum fluctuations. And we will assume that the field fluctuates only around its classical counterpart. So that's why we are allowed to do this. So we will assume here that each of the saddle points and the associated quantum fluctuations do not interact with each other. So we can write the total partition function as a sum of the individual partition functions associated to each saddle point. Because as I told you, this is the key point of the problem, that we have several saddle points that are relevant to obtain the final result. So just in case there is some people that don't know, or some PhD students, each of these partition functions will have this form that you see here. So we will have this exponential, and here inside will be the classical solution, the classical action associated to each of the classical solutions that we have. And here we will have the fluctuation factor, which will be computed at one loop. So the one loop approximation enters here, but it's true that this semi-classical approximation will give us some non-perturbative behavior. Okay, so which are the relevant saddle point configurations in this context? So we are focusing only on homogeneous configurations, so we will only consider time-dependent saddle points, because it can be shown that they are in this context with finite volume and true degenerate minima, that they are the ones that contribute the most. So we will focus in classical solutions to these equations, which is written already in Euclidean time. So which kind of saddle points we have? we have two types. We have the saddle points, which are the two minimum, and then we also have the instantons. The instantons are classical solutions in Euclidean time that can connect in several ways these two degenerate minima. So maybe it's easier to understand if we realize that when we work in Euclidean time, we have, instead of having this potential, we have this upside down potential. So then it's possible to connect these two minima in Euclidean time. So for the instanton part, as I will show you in the next slide, we will have several possibilities, an infinite amount of possibilities. And for the static saddle points, we will only consider these two of them because they are like the relevant ones. Okay, so one important comment, as I told you before, to compute the full effective theory, the full effective potential, we need to add this external source and play a bit around. But now I think because it's simpler and because it's the thing that gives us the relevant effect, I will focus in J = 0, which will correspond to the vacuum state of the theory or the vacuum energy that I showed you before. So in this case, the structure of the solutions is kind of easy. So on one hand, we have the static saddle points, which are these two minima, and then the action associated to them is, well, usually it's 0, but here, because we added this cosmological constant-like term, we have this that you see here, and T is time, is not temperature, sorry. Then we have many solutions that connect these two minima, but the basic solution, the fundamental solution, is this one, this canate, this one that you see here, and we also have the opposite one, with the opposite. And then the action associated to this solution is this guy here, where this S0 is proportional, the time dependence disappears because we have this integral, but this is proportional to the cell volume in which we are immersed. So that's not the only possibility, because we can also have multiple jumps that are solutions to the classical equations of motion. So the exact solution is hard to find, but this approximate solution works very well. So we work with the solution, and it can be shown that when we have like several jumps, let's say P jumps or P kinks, the classical action of the solution is the same that with one jump, but then multiplied by the number of jumps. Okay, so yeah, I said it here. Remember that this S0 is proportional to the volume, so all this effect is kind of irrelevant in infinite volume. Okay, so now let's go back to the partition function and let's try to obtain an analytical expression. So as I said you before, we can, the semi-classical approximation means that we can have the partition function and expand it like in all these classical configurations. So here I have schematically written all of them: one minimum, the other minimum, one jump, the anti-jump, two jumps, the opposite configuration, 3, 4, 5, 11. And here, each of these terms corresponds to the partition function of each individual classical configuration. So as I told you before, all of them should be like this. So this exponential and then this fluctuation factor. So for the homogeneous configurations, we just have this because, well, we can always take the normalization conditions to have this form here, and then the structure of the instanton part of the jump solution is very interesting because here one thing that I didn't told you before is that, okay, I plotted here the case where the jump happens at t = 0, but actually it's also a solution, the jump that happens here before, after, whenever. So we have all this degeneracy where the jump can happen anywhere. So then if we compute this contribution, this partition function, we find the following nice structure. This t time comes from the fact that the jump can happen everywhere. And then we realize that we can split this total thing in two parts. So the homogeneous part, where the field is most of the time, and then the jump part, which I call I. So here we have again the exponential, the classical part, and this is the one loop correction, but in a simplified version. Because for this first problem that I'm showing you, we only considered homogeneous quantum fluctuations. So then there is something that is missing here, but I will show you how to update this result. Okay, so we have this structure here. This comes from the zero model as usual. And we have this nice structure that is like, I will say is very, very nice here. For n jumps, for the case where we have n kings or n-type kings, we also have this possibility of having the jump in every side. And we also realize that the real scalar field spends most of the time in one of the other minimum. So we find very easily that more or less the structure for the classical solution corresponding to n jumps is this that you can see here. So now if we take all these results into account, we realize that the partition function in this semi-classical approximation can be exactly resummed. So we can do this and we find this very, very, very nice result that you can see here. So we have an exact result after several approximations, of course, of the partition function. Okay, so how can we compute the vacuum energy from this partition function? So, well, because I'm showing you the results for j equals 0, this is actually the vacuum energy. So we do this operation, and after working a bit with the quantities we have, we obtain this result, which is the U0 I showed you before. So this is the vacuum energy. So as you can see, we have this constant term. This is the standard term that we have, that we usually set it to 0, but in gravity it can be relevant as it can have a role for the cosmological constant. And then we have this very, very interesting correction that comes from the fact that we have this tunneling between these two degenerate minima in finite volume. So now, if we want to obtain the full effective action or the full effective potential, we really need to include J and repeat the process that I showed you before when we have in the classical equation a J here. This is then the potential shifts a bit, so it's a bit more complex, but it can be in principle done. So then how do we obtain from this the effective theory? So this is a process that most of you know, some of you may not know, but it's all established in quantum field theory. So from the partition function, we can obtain this effective theory, this effective action in terms of the effective field following these steps. So first we define the effective fields in terms of the source. Second, we invert the relation. And third, we apply this Legendre transform. So everywhere where we have J, we write J in terms of the classical field, and we apply this transformation, and this gives us the effective action in terms of this classical effective field that carries inside all the information about the quantum, the fact that the vacuum is quantum, so the theory is quantum, sorry. Okay, so this is like the steps are clear, but in practice it's very hard to do analytical computations to obtain this result because the relations are quite involved. But what we can always do is to obtain an expansion for small j. So if we only focus in small j, so the solution should be very similar to the vacuum solutions, we can have this relation, we can find this relation between the classical field and the source. So they are linear, which means that when the source is 0, the classical field is 0. So this is telling us that we have the minimum located not at V, not at minus V, but at 0. And then if we compute the corrections to this vacuum energy, we can see that the effective potential is like this. So we have, it's true that we couldn't obtain the full effective potential, but we can see that it has only one minimum. We can compute the vacuum energy, and we can see this kind of nice shape that we have. So then around the minimum, the effective action reads like the vacuum energy that I showed you before, plus these corrections. And then we can do expansion in J and then obtain corrections here. But okay, as I told you, we are really interested in this bit that you can see here. So, okay, now let's be a bit more realistic. I so to obtain this result, because we really wanted to see like the structure of the problem, we made some simplifications, or a lot of simplifications. So we are trying now to improve some of them. So the main result, before I was showing the result in terms of the energy density, because this was more useful for cosmology. But the main result, I would say, is that the vacuum energy that we can compute is this combination. This is the static vacuum energy, which usually is, which is the standard constant that we can have. And then all the contribution from the instantons from this quantum tunneling appears linearly here with this negative sign here. So the static contribution, because we are ignoring the Casimir effect, it's just this constant that we have here. And then the contribution from the instanton side is this bit that you can see here, where this is, again, proportional to this series proportional to this cell volume. So so we made some simplifications. I already told you, but I'm telling you now again. So for example, one thing that we did is like, we ignore the fact that when we work in finite volume, the momentum is quantized. So we have to consider the Casimir effect. So we have to correct this result and not having only the constant contribution, but really having this effect that comes from the fact that the space is finite. And then for the instanton side, for the instanton contribution, this result is obtained when we ignore quantum fluctuations. So we consider only homogeneous quantum fluctuations. So we compute the result in quantum mechanics. So we really need to be more accurate. We need to do this computation like better. So the questions that we are trying to answer now are, how would this result change if we don't ignore the Casimir effect? How would this result change if we consider the full quantum fluctuations? So we are working on this now. This is work in progress. Well, some part of this Casimir effect has been already done by many people, but in our collaboration by Drew, one of the PhD students. But we are also working on all these issues with Wenyuan, Jean, Matthias, and Björn. So considering momentum quantization, as I told you, implies considering the Casimir effect. So we have to make another change to the vacuum energy, and it shouldn't be just the standard constant that we can have, but we have to include the Casimir energy that is defined like this, as you can see here. So is as we all, I think, know, is the difference between this discrete sum and this continuous integral. And what happens with the Casimir effect is that it's strongly dependent on the geometry and on the topology. For example, for a 3 torus, let's say for periodic boundary conditions, it's found, or we found, or it's known that the Casimir energy is always negative, and it's bigger almost always than this contribution from the instantons. So it means that if we consider like a 3 torus as our universe, we have to make clear that the Casimir energy will be the Casimir energy is a quantum effect that can also induce a bounce, and that can be more relevant than the effect that we have considered so far. So for example, in this case, maybe we can say that, yes, what we did is correct, but maybe there are other effects that are as relevant or maybe more relevant. Now, the good and the bad thing about the Casimir energy is that it depends a lot on the geometry and the topology. So for example, I think if we consider a 3-sphere, then this result is kind of different, and this energy is not always negative, so we can have some interplay. The other thing that I wanted to tell you is that before, as I said you like 2 times, we only consider quantum fluctuations, homogeneous quantum fluctuations. So it means that in this computation that I showed you the final result, we ignore this bit here. But actually, if we want to be realistic and we want to work in 1+3, we have to compute this 1+3 fluctuation determinant. So this is what actually I'm doing with these people. It's almost done, and we saw that luckily So the full computation just gives us a small correction to the result I show you. So it means that the factor, the I that I was showing you before, is indeed capturing the main contribution from the instanton. So this is good news for our computation. Okay, so I think that's all. That's the end of the talk. I hope you like it. So let me summarize the conclusions. So we here try to study quantum tunneling, but instead of focusing in false vacuum decay, we kind of focus in this configuration where we have finite volume, pseudo-degenerate minima, and then we allow tunneling to happen between these two minima. We computed the effective theory, and this effective theory is very, very nice because we realize that it's quite different to the classical theory. It only has one minimum, one true vacuum that has some non-trivial properties, some non-trivial vacuum energy. In particular, it violates the neck, so it can be potentially relevant in cosmology. In particular, it can induce a cosmic bounce. So I would say this solution is nice, but it's limited. So it's nice in the sense that it's an effect that favors expansion over contraction, because this effect only activates when we are very close to the singularity, but for big volumes, it's exponentially suppressed. So it's a mechanism that favors expansion over contraction. And another nice thing it has is that I think it's quite independent of the topology and geometry. So I think it will be negative always. So it's true that the Casimir energy can dominate, but I think this is a safe thing that we may always have in this context. Also, it's not ideal because we see that when we start to including like some complexity to the system, then the bounce doesn't happen necessarily. So for example, we saw that when we include anisotropies, the bounce can still happen, but it's not always the case. So this field is not a smoother. It's not something that can cancel on time the anisotropies, so then guarantees like the bounce. Last thing is that we, like as a future work, we are making like adding complexity to this model and to these ideas. In particular, we saw that when we improve the computations of this fluctuation factor, we don't get significant corrections to the results I showed you. So this is good news for the analysis we did. Also, and yes, the Casimir effect, when we consider it like properly, we see that sometimes it's more important than the effect we have, but it's the same type of, I would say it's the same type of effect. So the Casimir effect violates the neck, so then it can induce a cosmic bounce in the same way I explained you here. So I think that's almost all. Thank you. And yes, I'm happy to answer questions.
Thank you very much, Silvia, for the great talk. That was really interesting. Let me just open this up to the floor. Are there any questions? So the first one I saw there was Anna Kormu. Anna, if you'd like to go ahead.
Yes, so I actually have two questions, and thank you for the talk, by the way. Could we go back to slide 8?
Yes.
I believe it was slide 8. Yeah, so you say here that we assume that periodic boundary conditions do not play a role. What exactly does that mean, and how can you quantify that in a finite volume?
I think this is some slide that I recycled, but now I think that what we did in fact is assume periodic boundary conditions. Because we were borrowing the results from, we were not considering the Casimir effect. We didn't care in that side about the boundary conditions. And then for the instantons, since we were borrowing results from quantum mechanics, we didn't care about the structure of the finite volume. But actually, now that we computed the full 1+3, I think what we were doing is that we were considering periodic boundary conditions. So it means that in the improved result that we have, for the instantons, this configuration is not allowed because we can only have pairs that start and finish in the same part, but it doesn't change the result. So let's say that we are safe.
Okay, thank you. And the other question is that can you elaborate a bit on the Casimir effect and how it plays into these calculations? I was a bit confused by that.
Okay, so okay, so yes, so I think for the Casimir effect, effectively, what will happen is that we will have an extra term here that will be, in the case of the three torus, for example, it will be also negative, and it will be also suppressed for large volumes. And for small volumes, it should go like 1 over a to the alpha to the 4. So it's like an extra negative term that you can have here that appears just when you compute this V, taking into account that the momentum should be discrete. So when we consider the fluctuation factor here, it appears naturally. So in practice, after some algebra, you can see that the relevant contribution is just this one. So this difference, and it gives you, because here you are summing and here you are doing an integral, you will have a non-vanishing result that is in fact negative, that will appear in this way. Minus sign for small volumes, 1 over a to the 4 in the energy density, and for large volumes, suppressed linearly with the length, typical length of the system you're considering.
Okay, thank you.
Okay, we have a number of other questions. Ian Moss.
Oh, hi. Oh, thanks, Sylvia. That was a nice talk. I enjoyed it. I have two questions too. The first thing is, it's a technical question. The partition function is a function, right, of the source J. I'm just concerned about how can you extract any information out of J at 0 when it's just a number, and one that we usually just normalize by anyway.
Well, I'm not sure if I understood the question, but like, well, when J is equals 0, you still have some saddle point structure. So you can still have some information about the vacuum energy, right? So this is, all this analysis still holds. So it's true that you can't do this, but you have this, you can obtain this. So I guess this gives you the vacuum energy at the end of the day. But I think
yeah.
Yeah.
I'm sorry to interrupt. Can I make a suggestion? That there's a nice way of extracting information from J at 0. That is, if you differentiate it with respect to the metric, you'll get the expectation value of the stress energy tensor. So I suspect that's what guarantees that you probably gain the right answer here, because ultimately you can extract information from J at 0, but it's a bit dangerous because, like I said, the path integral measure is always arbitrary up to a constant anyway. So it's a bit dangerous trying to extract something out of a number. But if you just differentiate this with respect to the metric, you'll get back the stress energy tensor. So I suspect that's perhaps a more rigorous way of getting information out of that. Okay, the second question is more fun. Have you thought about applying this to the interior of a black hole? I mean, obvious extension there.
No, but I'm open to talk about it.
Give it a try.
Okay. I write you an email asking a bit more in deep about this idea. But okay. Thank you.
Thank you very much. Yutaro.
Hi, Silvia. Just can I some question about the is it possible to understand this effect? It's kind of in the analogy of some molecular-like thing. So if you have the some degenerated I mean the states, then if you have the hopping between them, then actually the vacuum decay or the energy just goes down, and actually it's the molecule bounce, and probably maybe this is the kind of a similar effect. But is that true? Or?
I didn't know about that, but it makes sense, right? I think it's like this should be the quantum mechanics analog to the thing that I'm saying here. So I think it makes sense.
Thanks.
Thanks, Yutaro. And Lucian?
Okay. So I have two questions as well. So the first, maybe I missed it, but you said you were assuming some kind of adiabaticity, like the Hubble rate was always yeah, that
Yes, 0, in fact.
tunneling, yeah, small compared to the tunneling rate, right? Did you have a way to check that in your bouncing cosmology scenario?
So I think yes. So I think if you then you should check. Of course, you should check some rates to see if how good is the approximation. I think you can compute well in this when you have the metric and everything H dot
Right.
and see.
Yeah.
But it's true that it's a problem that we can't have staticity, because like in this so for example, I think in this case when I added the anisotropy, we were safe because we were able to obtain a critical solution, a critical size. So this is self-consistent, right? Because we have always H dot equals 0. So then the ansatz is perfect, or the initial idea is perfect. But I think you are right that we should be maybe it's a next step that we should do is to see how good is this adiabatic approximation. But anyways, the problem is that I don't know yet how to compute this if I consider out of equilibrium field theory, because it's like I think instantons are strongly related with, as far as I know, with weak rotations. So I think it's not trivial to see how work with these two time scales, given that one happens in Euclidean time. So you are right, we have to check. We are not safe, but it's hard to see how to improve this computation.
I thought your approach made sense. I mean, if your expansion rate is small compared to the tunneling rate, then you could still use the Euclidean formalism and ignore the expansion rate, and then see what dynamics you obtain for H, right?
Mm-hmm. Yes, but at some point maybe you have a breakdown, because maybe you have a complete But well, we can say that at some point this effect is suppressed anyways because of the exponential, so we can naively say that we are safe. But yeah, you're right.
And the second question is maybe a little bit naive, because I was not familiar with the thing you presented of like the two minima being like turning back and forth to each other. I was wondering may I think of this as a way to approach the full effective theory in a smart way? Like if I take a potential and I expect the full effective theory to have a convex potential, right? But if you just do a one loop calculation, you with this kind of potential, you don't get something convex, right? But you actually do. So I was wondering if I may think of what you do as a way to approach the effective theory.
I think maybe yes. Maybe the thing that we are doing of this fact that we are taking into account that the partition function can be approximated in this way, like considering all these solutions. Maybe it's what's giving us some insight about this full quantum theory that is indeed like with only one minima. Yes, I think if you do the same, but in the case you are used to with this false vacuum decay and try to compute to repeat this, you will have one minimum but located at the false vacuum. After if we try to do a similar analysis, but then the full effective theory, like I think you will have only one minimum located at the plus B, let's say, I think. So
thank you.
Okay, thank you very much, Silvia. That was a very interesting talk, and thanks for all the questions, very interesting questions. Next month, on the 14th of March, we have Yutaro Shoji, who's giving a talk entitled Gauge Invariance and Gauge Zero Modes of Bubble Nucleation Rates. So yeah, we look forward to that. Thank you again, and yeah, see you in a month.
thank you.